In this video, we're going to go over section 2.3 from our textbook, which talks about more transformations of graphs. And the first kind that we're going to look at is called vertical stretching. And so if we have some point x comma y and it lies on the graph of y is equal to f of x, then we know that it must be the case that this point here is going to lie on the graph of y is equal to c times f of x. Now, if this c is greater than 1, then our graph y is equal to c times f of x is going to be called a vertical stretching of our original graph y is equal to f of x, because we're applying a factor of c to this guy. So this graph here on the right shows this exact scenario. So if we have our original function here, y is equal to f of x, this is what it looks like. And we have our point x comma y here. Then if we were to apply a factor of c to our function, this is our new point, so instead of x comma y here, we get x comma c times y. So we're just applying a factor of c to f of x, so our output changes. And if we were to do this to every single point on y is equal to f of x here, we would see that our resulting graph is this blue curve here. So every single point here is being vertically stretched in this direction, and every single point on this curve is being vertically stretched in this direction. Okay, so we kind of think of it as being vertically stretched about our x-axis. So everything on this side of our x-axis is being vertically stretched upwards, and everything below it is being vertically stretched downwards. So let's look at this example here. We have our original function is going to be y is equal to x squared, and it's given by this green parabola here. And if we were to apply a factor of 2 to our function y is equal to x squared, it would result in this parabola here. And so this blue parabola is vertically stretched, or we're actually vertically stretching this green one to get the blue parabola, and it results in a more narrow shape. So this tells us we're vertically stretching the parabola by a factor of 2. All right. And we can test this by looking at a few points on our original graph. If we have y is equal to x squared, we know if we plug in 1 here for x, our output would just give us 1. And so that's this point on this parabola here. However, if we were to plug in the same value for x into our new function that's changed by a factor of 2, we would get 1 squared and then multiply that by 2. So our output would now change to 2. Okay? So this point here is now stretched and is this point here. And we can do that for every point along this parabola, and we'll see that it'll result in this blue parabola here. And this is what it looks like when we were to vertically stretch this guy. All right. If we can have vertical stretching, we can also have vertical shrinking. So again, if we have a point that lies on this graph, then this new point here will lie on this graph as well. So we're just changing it by a factor of c. But if this factor of c lies between 0 and 1, then this new graph is called a vertical shrinking of our original graph, and it's a vertical shrinking of a factor of c. So again, if we have our original function here, this black curve, and we were to apply a factor of c that's in between 0 and 1, then this graph shrinks vertically. So instead of stretching it or pulling it in this direction now, we're kind of pushing it down in this direction. So this would be our original point that we were talking about, and then by applying the factor of c, this point is pushed towards the x-axis. Okay. So let's look at another example with this parabola here. So we have y is equal to x squared, and that is given by this green parabola here. I'll label that. And then the blue one is our new graph, where we are applying a factor of 1/2 to our original function. And so just like how we did in the last example, We can see what happens if we were to plug in values for x. So again, if we were to plug in 1 for x here, in our original equation, we know that we would just output 1. So this is our original point. But when we apply this factor of 1/2, if we were to plug in 1 for x, we would get 1 squared multiplied by 1/2. So our output in this case on our new graph is this point here. Okay? So every single point on our original parabola here is being pushed down or vertically shrunk. All right, and then again, you can do that for all the points on the parabola, and we'll see that it'll result in this blue parabola here. So in this case, we're vertically shrinking the parabola x squared by a factor of 1/2. All right. Now with that, we're going to go into horizontal stretching and shrinking. So by the same logic, if we have a point that lies on this graph here, then this new point must lie on the graph of this guy here. And then we'll have two cases. If this factor c is in between 0 and 1, then this new graph here is called a horizontal stretching of this original function, or original graph. And then if c is greater than 1, then this new graph here is called a horizontal shrinking of our original graph. Okay, so instead of multiplying our function by a factor of c, this factor of c is going to be applied to our function. Applied within our function, sorry. So here's an example of a horizontal stretch. So now instead of with vertical stretching, we were kind of looking at it as stretching about the x-axis, so pulling everything away or pushing towards the x-axis. With horizontal stretching or shrinking, we're going to think about pulling or pushing towards the y-axis now. So for a stretch, everything's going to be pulled in this direction or this direction, and then for a shrink, everything will be pulled this way and this way. All right, so let's look at a few examples here. So just keeping with the parabola here, if we originally have y is equal to x squared, and we have this new function here, y is equal to 2x squared, so this factor of c here, this 2, is within our function. We have a power function here, and this is being applied to within our function. Before, with vertical stretching and shrinking, this factor would be on the outside of our function, so we would do our x squared first and then multiply it by that factor. In this case, we're going to multiply x by a factor of 2 and then square that. All right, so let's look at our same example. If we were to plug in 1 into our original x squared function, we know we just get 1 out, so that would be this point here. But now when we horizontally shrink this guy, we'll plug in 1 for x, so we get 1 times 2, and then we get 2 squared. So that ends up being 4. So this point here now becomes this point here. All right. And this would be horizontal shrinking because we're pushing everything towards the y-axis. Now for this example here, our c factor is 1/2, so it's in between 0 and 1, so we know that this is going to be a horizontal stretching. And again, looking at x is equal to 1 here, so this should be 1. We know our output is just going to be 1 when we plug in x into our original function. But if we were to plug it into our horizontally stretched function, we would plug in 1 here, and we would get 1/2 times 1, which is just 1/2, and then we would get 1/2 squared. So if this line here, so this is about 1, so this one's probably about 1/2, so that makes sense that our point is half of that, 1/4. So this point here becomes this point here because we're pulling or stretching this graph in this direction here, horizontally. And again, if we were to do that to every single point on our parabola, we would get this blue parabola here. All right. Now the last transformation we're going to look at is reflecting a graph. So if we have this function y is equal to f of x here, then the graph y is equal to minus f of x is going to be a reflection of our graph across the x-axis. And then if we have the graph y is equal to f of minus x, this will be a reflection of the graph across the y-axis. So here are two examples of this. This blue curve here is going to be our original graph, and if we were to reflect it across our x-axis here, so we're taking minus of our original function, every single point here would be exactly reflected across our x-axis. So this point becomes this one, this one, this one, and this one becomes this one. Now similarly, if we were to start with our blue curve here, and we were to take f of minus x, everything would be exactly flipped over our y-axis here. So this point becomes this one becomes this one, and this one becomes this one. All right, so what we're going to do now is just go over one example where we are going to apply everything to this function. So everything we just went over. So we're given this function here, which is defined on this interval, and it can be showed by this graph here. And the first thing we want to do is identify the graph transformations. And I believe in your homework, it'll ask this by saying how f of x is obtained from your original function. So it should give you your original function here. And that is should be somewhat obvious from just looking at f of x because we have this absolute value here. So we're going to do some color coding. So we have this 1/2 applied to our function. So this tells us we're going to vertically shrink our original function, so our absolute value of x, by a factor of 1/2. Okay. If this 1/2 were inside this absolute value function, then it would be a horizontal stretch. All right. Then we have this -4 inside of our absolute value function. And if you remember from last video, this means we're going to have a horizontal shift by 4 units. And that's going to be to the right. And then lastly, we have this +2 on the outside of our function. So this means we are going to have a vertical shift now. And that'll be 2 units up. All right. And we can check this by looking at our absolute value function. So this guy looks like this here. And if we were to apply these transformations here, we would end up with this guy. And we can do that just by plugging in values for x, like how we did with the parabolas in the past examples. All right. The next thing we want to do is sketch the graph of y is equal to minus f of x. And if you remember, if we're looking at minus f of x, that means we're going to have a reflection across the x-axis. So we're doing a reflection across the x-axis. So let's do some more color coding. We're going to reflect across the x-axis. So every single point on our original graph is going to exactly reflect across our x-axis here. And you can kind of think of this as just by looking at the negative of what our original output value was. So we have a 2 for our x value, and our original output was 3. So that means when we reflect across the x-axis, we're still going to have our input as 2, but our output now is going to be -3. Okay. Then we're going to reflect this point across our x-axis. So remember, our input value is still going to be 4, but our output value is just going to be -. of what our original one was, so minus 2. And then doing the same thing for this point here, 6, 3, we'll get 6 minus 3. Alright, and so let's just label these. And so this is our graph reflected across the x-axis. Alright. Then we want to do the same thing. We want to sketch the graph of our original graph reflected across the y-axis. So now in this case, our output values are not going to change sign, but our input values are. So we're reflecting this guy across our y-axis, this guy here, so reflecting across this one. And we know that when we reflect across our y-axis here, our x values are going to change sign, but our y values are not. So this point here, 4, 2, is going to become minus 4, 2. All right. And then this point here, 2, 3, is going to become minus 2, 3. And lastly, we have 6, 3, so reflecting this across our x-axis, we're going to have minus 6, 3. And sorry, reflecting across our y-axis. So this is our graph reflected across our y-axis here. All right. And then we also want to give the equation of these guys. So we know that we'll just take our original equation for this one and take the opposite of that. So our original equation was 1/2 x minus 4 plus 2. And so we're going to take the opposite of this. So like that there. This will become minus 1/2 times absolute value of x minus 4, and then minus 2. And then the equation for part C here, our input value is going to be negative. And our original equation was this guy here, 1/2 absolute value of x minus 4 plus 2. So this just becomes minus x minus 4 plus 2. Alright, so that's going to be it for this video.